Hello, everyone. Welcome back. We're starting a new unit today. Um, this unit is titled Geomorphology, and so I'm going to break down the term geomorphology, but in this unit, what we're basically going to be doing is looking at some of those processes on the surface of the planet that change it in different ways. So up to this point, we started with, of course, the study of rocks and minerals. Then we moved into historical geology and looked at how we know what we know with relative age dating and absolute age dating techniques. And then we got into dynamic earth processes. Dynamic earth processes are those things going on under our feet, those major processes that transfer energy and matter and move it all around and uh, end up creating things like earthquakes, volcanoes, and then of course plate boundaries and uh, the process of mountain building and the creation of those volcanoes and trenches and all those other different landforms. So geomorphology, geo meaning earth, of course, morph meaning change or study, or excuse me, change, and then ology is study. So we're really looking at how the earth changes throughout time and some of those processes that transfer matter and energy on the surface of the planet. It's kind of a continuation of historical geology, rocks and minerals, and dynamic earth processes, but here we're really looking and focusing on the surface and using the clues that we see and our understanding of different processes of weathering and erosion to end up how we look today. So it's a really interesting topic. It's this whole separate form of geology, but really cool, really interesting things that are happening that we kind of take for granted because they can happen on such long time scales. But it's also a very powerful study, very similar to plate tectonics, in that we can look at an area and say, okay, this is what happened here. This is why we had this strange looking U-shaped lake. This is why we see these strange collections of hills that are teardrop shaped. So geomorphology is really powerful in that you can predict and hypothesize and theorize how the earth became like it is and how different parts of the earth appear like they do. So let's get into geomorphology. Today we're just going to be looking at the primary processes of weathering and erosion. So geomorphology. Just like before, we start with our systems definition. A system is processes that transfer matter and energy. And these transfers of mass and energy can result in chemical and physical changes, very similar to chemical and physical weathering. And these processes can be ongoing. They can be one-time events, or they can vary on daily, seasonal, yearly, other periodic cycles. So in geomorphology, we're really looking at and honing in on those things, those processes that change the surface of the planet based on those four systems that we've talked about, the biosphere, the hydrosphere, the atmosphere, and the geosphere. Also the anthroposphere, can't ever forget that one. So we're going to start with weathering, and then we'll move on to erosion. But weathering, you probably remember this from earlier sciences. Weathering is the opposite of lithification. Lithification is the creation of a rock. Remember, in sedimentary rock, erosion, deposition, compaction, and cementation, that's lithification. And of course, your igneous and metamorphic rocks. Metamorphic rocks are lithified by heat and pressure. Igneous rocks, of course, are cooled, or the magma or lava is cooled to create the rock. Weathering is the opposite. Weathering is the breaking it down into smaller pieces and smaller chunks. And there's two types. There's mechanical weathering, which is a physical change. You're not changing the rock chemically, you're only making it smaller. And then chemical weathering, which is a chemical change. You're breaking it down into smaller pieces through chemistry. So we'll start with mechanical weathering. Again, it's a physical change in the shape or size of a rock. And the major agents of mechanical weathering are ice wedging, abrasion, and organic activity. So let's start with ice wedging. This is really cool. Happens a lot in temperate and cold climates. So in ice wedging, water seeps into cracks in the rock. The water freezes and expands. One of the cool things about water is that when it does freeze, it actually expands in volume. So that can put pressure on the rock, causing it to crack into smaller and smaller bits, just like the diagram here. You can see this really cool shaped round rock that is starting to crack. Over time, these pieces will fall off. Again, you can see that happened here and here. It can actually split the rock. If you've ever been driving up in the mountains in the fall, and I've done this quite a few times, and we go up to the mountains around Asheville, North Carolina in the fall, go look at the pretty leaves, and the road would be closed. The Blue Ridge Highway would be closed temporarily due to an avalanche, just a bunch of rocks that came down. And it always seems to coincide with the first hard freezes. So the rocks that are exposed on the side of the mountain, water seeps in, it freezes, expands, breaks the rock, and of course it comes tumbling down and covers the road. So ice wedging is very powerful in that it breaks things down in cold climates or temperate climates where you have seasonal changes. Abrasion is the process of collisions. So rocks smacking into each other, smashing them into smaller bits. Again, you're not changing it chemically, you're just, bam, breaking. Abrasion can be caused by gravity as things roll downhill. Running water will carry sediments and other pieces of rock. Sorry, my dog's going a little crazy. And ice, movement of ice like a glacier, or wind. As wind moves, it picks up sediments, and you can see in this diagram, the sediments will hit and break off other pieces which can fly off. Abrasion is what caused this column, and if you've ever seen this picture or pictures like this, these are sandstone, and it was wind that caused this, not water. Wind actually picked up the small sediments, and as it blows through the area, it breaks it into smaller pieces and smooths it out. Abrasion, just like sandpaper, but in this case, we have wind or water or gravity. Organic activity. This can be both chemical or mechanical, but in terms of mechanical weathering, organic activity is referring primarily to root activity. So as a plant grows in the spaces, small spaces inside of a rock, as that plant grows, it'll put pressure on the rock, and over time can split it, just like in these pictures. So the roots themselves act as a mechanical agent, breaking apart the rock into smaller pieces. Exfoliation. This is a neat one. If you've ever seen pictures of like Yosemite National Park, and you'll see that it's kind of got this weird expanded pieces, or kind of like an onion or peels. Exfoliation occurs when strong rocks have been removed off of a surface of other rocks. And so the weight, once that weight of or mass of rock has been removed, the underlying rock can expand, and it expands, it'll break, crack and peel like an onion. It's really neat looking. If you've ever been to the James River, the James River in Richmond shows lots of exfoliation examples all throughout. People used to mine the rock there, and so they would cut these huge pieces of granite and move them out of the way. Well, the cool thing is, once it's been removed, you can't put it back because the weight of that rock was held in place. Once that mass was removed, the rock actually expands and cracks. Also, just the typical abrasion, removing rock off the top over long periods of time. Once that mass has been removed, the rock will expand and crack and look like an onion. It's really neat, sheet-like. So that's mechanical weathering. Chemical weathering involves a chemical change. It is some kind of chemical reaction that can change and break down the rock. So here are the primary agents of chemical weathering: oxidation, hydrolysis, carbonation, acid rain, or organic chemical weathering, which is from plants or from animals growing in and around the rock. So start with oxidation. This is really simple. Rust. So iron-bearing minerals in the rock will react with oxygen in the air to form rust, Fe2O3. The clay in the Piedmont, that red coloration of the clay, is due to oxidation. So the rock has been chemically altered. It becomes looser and will, you know how clay acts. It's very small particles, gets in your clothes and never comes out. But oxidation, rust. Hydrolysis is a form of chemical weathering where water is actually absorbed by the minerals in the rock, producing a weaker material. So um, the only common rock that's really not affected by hydrolysis is quartz. It's very chemically resistant, SiO2. Um, However, the other minerals like feldspar, that's also found in granite, is highly susceptible to hydrolysis. It will absorb the water, become weaker, and start to flake off. Um, there are other minerals that are very highly susceptible as well, but hydrolysis is where water, it's pulling in that water, it's chemically bonding and becoming weaker. Carbonation, this is a big one. Carbonation is when carbon dioxide from the air dissolves into water. It becomes a weak acid called carbonic acid. Limestone is highly susceptible to acids. So over time, what happens is the limestone is slowly dissolved by that water, that weak acid. And so it will form caves, stalactites, stalagmites, Luray caverns, for example. As the groundwater moves through the permeable rock, it dissolves the limestone and then transports it somewhere else. So carbonation is really, really powerful and creates its own unique landforms. It's called karst topography. Common in the valley and ridge province, can form sinkholes, caves, stalactites, stalagmites. But again, as the water permeates through the rock, the carbonic acid, the weak acid dissolves the limestone. And so then you have these huge caverns and spaces. And as the water drips from the ceiling, it leaves a little bit of mineral behind. And then when it hits the floor, it leaves a little bit more, creating stalactites and stalagmites. Organic acids. Organic acids are, just like I said, it's a living thing that secretes an acid that can help break down the rock. Usually it's a plant, or maybe it's lichen, which is, fungi and algae kind of living together in a symbiotic relationship. They secrete these acids to attach to a substrate, a rock, and very slowly over time, these weak acids can break the rock down. Even animals burrowing into the ground, saliva, acids, enzymes can help dissolve the rock very, very slowly, of course. Even fecal matter, urine, all of those can act as an acid and corrode minerals in the rock. All right. Another big one, acid rain. So industrial pollution, carbon dioxide, sulfur compounds in smokestacks, and even volcanic activity, volcanic gases like sulfur dioxide can actually dissolve in rainwater. And so once it's dissolved in the rainwater, the rain itself becomes a very weak acid. Over time, this can operate on different minerals and rocks that are susceptible, things like limestone as well, and will break down the rock. Here's a little quick way to remember it. Mechanical weathering typically occurs in cold and dry climates. Chemical weathering tends to happen in hot and humid climates. And that kind of makes sense because chemical weathering operates a lot with water, hydrolysis, oxidation, carbonation, creating karst topography. All of those involve water. So humid environments really can chemically weather. Whereas in mechanical weathering, you have more wind, abrasion, and of course, ice wedging. So cold and dry is more mechanical, chemical is more hot and humid. Here's a quick case study for you, Cleopatra's Needle. So there's a red granite monument in Egypt, stood for 3,000 years. In 1881, it was gifted to New York. I think it was put in Central Park. So the obelisk had been sitting in the hot and dry desert climate for thousands of years. It moves to New York, where the climate is very different. you have more humidity, you have more moisture in the air. It started to chemically break down. So as a result of chemical weathering, you can see what happened. There's one side or two sides of the needle now that you can't even read anymore. Wherein before, in Egypt, up to 1881, you could. And the cool thing is that it's on the west and southern sides of the obelisk that are most weathered, because that's the prevailing direction for storms. So chemically broken down. Whereas when it was in Egypt, it was hot and dry. You didn't have that chemical weathering. Never had ice wedging either, but now you do. Now it comes to New York, it has temperate climate, lots more humidity, and it's been broken down very quickly. So weathering is breaking down. Erosion, and a lot of people get these mixed up. Erosion is actually the movement of material. Erosion is any natural process that removes sediments and moves them from one place to another. So erosion is the actual movement. Weathering is the breaking down. There are some primary agents of erosion. Glaciers, rivers of ice, basically, running water, rivers, wind, and then mass movements. So we'll take a look at each one. Starting with glaciers. Glaciers are basically rivers of ice. They, of course, occur in cold climates. They're affected by gravity as they roll downhill. Here's the cool thing about them. They pick up sediments, lots of sediments, from small sediments, pebbles, smaller, silt size, to boulders. As they pick up the sediment, they roll and they tumble. On the sides of the valley where they're coming down, they can scrape into the rock. They're really neat, and they really leave telltale signs that they were there. So after, let's say, plate movements, we have a cold area that's now a warm area. They leave behind lots of evidence. For example, glaciers carve U-shaped valleys. So when you look at a valley, if it's shaped like a V, it was not a glacier. That's actually a river. But if it's shaped more like a U, that's a glacier. When that glacier retreats, or the climate changes and it warms up, it leaves behind all of that sediment, and it's very unique in that the large and the small have all been tumbled and rolled, so they're very smooth. And so when it retreats, it leaves big piles of this material. Also, as the glacier moves, it cuts into the rock itself, and sometimes the rock is harder. And so when it retreats, it leaves these weird teardrop-shaped hills that you can actually look at and tell which direction the glacier was moving. There are other landforms as well. If we have time later in the year, we'll come back to glaciers and we'll really delve into them. But glacier erosion is one of the big agents. Rivers, of course, are also the other big one. Rivers create V-shaped valleys, and you can see, if you look, and I know it bends, but if you look here, you can see this nice V shape. So as the river cuts down into the rock, it continually creates this V shape. Rivers are this whole separate study in geomorphology. They leave some really telltale signs that they were there. They change. There are parts to a river. Over time, the river, you can start with a pretty straight river, but it will curve and sometimes even eventually pinch, and then the river will continue that way, and you have this lake sitting off to the side called an oxbow lake. So river, of course, primary agents of erosion, moving material just like glaciers, but they also can cause abrasion just like glaciers, form of weathering. The only way to prevent rivers from erosion are generally roots. So plant roots, of course, can hold on to the soil and kind of slow that erosional processes rivers down. One big thing that I really want you to know about rivers, and it makes perfect sense, the faster the river, the bigger the sediment it can carry. So you can see in this graph, stream velocity from 0 to 800 centimeters per second. The faster it goes, the bigger the particle diameter it can carry. So if it's moving really fast, it can carry houses, cars, boulders. Makes sense when you look at tsunamis. So when you have a river that starts up high in a mountain is moving very fast, it can carry some very large material. As it comes down out of the mountain and the elevation starts to, the slope of the elevation starts to gradually decline, the river will slow down. As it slows down, it deposits all that stuff it was able to carry as it slows. So it may deposit really big stuff very high up in the mountain, and it just deposits smaller and smaller in sediment. By the time it reaches the ocean, the only thing it can carry, because it's moving so slowly, are very fine particles like silt and clay. This makes perfect sense because if you look at the rivers along the East Coast, there's a point. It's called the fall line. The fall line is this elevation change as you come off of the Appalachian Mountains going to the ocean. It is this quick change where we find rapids, waterfalls, lots of big boulders. If you look at almost all the major cities along the East Coast, primarily state capitals like Columbia, South Carolina, Raleigh, North Carolina, Richmond, Virginia, if you look at those, all of those cities are along the fall line. So it is that point where coming off of the mountains, it changes very quickly. And so you have these large rocks and boulders kind of set up. The rapids. And so the idea is that ships and boats could carry material from the coast all the way to that point. And from that point, they had to unload and put them into carts and then send them further inland to get up into the Piedmont and the Appalachian Mountains. So most of these state capitals actually formed because that was that point where you had to have warehouses and transportation for horses and carts and all that kind of stuff. So kind of a neat idea, but rivers, the faster they go, the bigger the stuff that they can carry. And so as it slows, it drops off smaller and smaller stuff, so that by the time it reaches the ocean, the only thing that it can carry is small little particles. Wind erosion and water erosion can both cause abrasion. So remember, abrasion is mechanical weathering where particles are smacking into each other. Wind erosion, or that movement, picks up the sediment, bashes it, keeps moving. So wind is both an erosional and a weathering agent. You can see all of these neat structures. Here's that sandstone I was telling you about. All right, last one as far as erosion. Mass movements. In mass movements, we're really talking about things like landslides. Either they're fast or they're slow. So a landslide in general is defined as the mass movement of rock, debris, whatever, coming down a slope due to gravity. Landslides are a type of mass wasting, which anything that rolls downhill in large quantities is what we refer to as mass wasting. So you can see in this picture, this really quick event, landslide, it just pours straight down. And of course, over here, we see the houses dropping. Now, there's different types referred to how they move. So one is called a slump. A slump is a form of mass wasting that occurs when a large mass, coherent mass of loosely consolidated material moves a short distance down a slope. So you can see in this area here that it just kind of slumps. I mean, slumps. So it moves pretty quickly, but it doesn't move very far. So it just kind of slumps down. Creep is very similar, but it's slow movement. So you can see in the diagram here where the electrical poles are kind of sideways, and you can see here in the fence where it's kind of sideways, where they were put up straight. Creep is that slow downslope movement, whereas a slump is much faster. Last one, mudflow. Mudflow is another form of mass wasting, but it's very rapid, extreme, and where the rock the rock and loose material acts like a liquid or has a lot of water or liquid in it. An example would be, let's say there's a glacier on a mountain Turns out the mountain's not a mountain, it's a volcano. And then there's an eruption. The glacier melts very quickly, comes down slope very fast, picks up loose material, and comes straight down, called a lahar, so mud flow. So lots of different reasons for this, but again, it's a form of landslide, a form of mass wasting where lots of material moves very quick pace. All right, believe that's it. So we've covered basically the primary things in geomorphology: weathering and erosion. Weathering, mechanical and chemical weathering. Mechanical like abrasion, ice wedging, and then chemical like oxidation, hydrolysis, carbonation, making karst topography. And then we looked at erosion. Erosion is the movement of that material. So movement from glaciers, from rivers, from wind, gravity, including landslides. So these are all things that shape the surface of the Earth over short time scales or very long time scales. So these are agents that leave behind telltale signs and constantly shape the world in which we live. Geomorphology, geo-earth morph change. All right, that's it for this one. And the next thing that we'll, I think, be looking at is specifically soil and groundwater. But if you have any questions, as always, please let me know. Thank you.